So in the last chapter, we talked a lot about acid-base types of reactions. We've been focusing quite a bit on equilibria, and in this chapter, what we're going to be focusing on primarily is just the applications of aqueous equilibria. Namely, that means looking at titrations. Towards the end of the chapter, we'll look a little bit about basically insoluble salts and seeing how they dissolve, and the equilibria constants that govern those, called the KSPs. But a lot of the early part of the chapter focuses on much of a sort of similar topic that we covered last chapter with acid-base equilibria. So with that, the first thing we want to really cover are neutralization reactions. And a neutralization reaction is just a reaction in which we have an acid plus base, and it's going to yield a water plus a salt. That's what we're going to see as the products there. One of the questions, which we sort of know the answer to because we talked about basically some of these reactions in the last chapter, but one of the questions that comes up is the result of of this sort of mixture of acid base, is that always going to yield a neutral pH? And the answer is no. It depends upon the nature of what we're actually mixing. If we are mixing a strong acid and strong base, then we do expect, in that case, like so for instance with HCl and sodium hydroxide to create water and sodium chloride, we expect a net ionic equation, which is just going to be H plus hydroxide to yield water. Now this is something that we haven't talked about in a little while, and that's just the net ionic equation, so hopefully you remember that. Remember, it's just basically the species that participate in the reaction. So if you imagine in reality, we have HCl and sodium hydroxide, but let's say before those encounter one another, it's just the hydronium or H plus ion floating around. It's the chloride is floating around merely interacting with the water. Sodium's floating around and hydroxide's floating around. They're all just separately just sort of floating around, even though you might have initially put them in together. They were just sort of floating around solution. But when the hydroxide and the hydronium interact with one another, they immediately form water, and then those sodium and the chloride, those would still be floating around in the solution. So if we're just looking at what actually changed, what chemically reacted, it was the H plus and the hydroxide to form the water. We have talked about what the equilibrium of water basically dissociating, and that was H2O going to H plus and hydroxide. And remember, I had the equilibrium arrow and it was governed by Kw. Well, if you notice, this neutralization reaction is the opposite of that. And we didn't draw an equilibrium arrow, we drew a solid arrow, which I'll just touch on in just a second. But you can see that for the neutralization reaction, if you were to treat this as equilibrium, it's just basically 1 over the Kw, because you would get 1 over the hydroxide and hydronium ion concentration. So that leaves us 1 over 10 to the minus 14, which is 10 to the 14. What do we expect to be favored when we see such a large number for equilibrium constant? We expect that the products are going to be favored. And so in a neutralization reaction, it's pretty safe to say if you have hydronium and hydroxide and they interact, it's going to completely go to products. So we don't have to treat it as an equilibrium in that case. So if we look at what we'd be left with, we just, after this reaction, we have water and sodium and chloride. And none of those species are going to be acidic or basic, and so we can assume safely that if we have a strong acid and a strong base, we will get a solution with a pH of 7. And just another thing to note is calling it out explicitly, Kn is just this equilibrium constant that we have for the neutralization reaction. So moving on, we want to look at the neutralization reaction between a weak acid and a strong base. So for example, we're going to use the the acetic acid plus sodium hydroxide being neutralized to form water and sodium acetate. So it still follows the same formula as we looked before. We're adding an acid and a base, and we get a water and a salt. The net ionic reaction will look a little bit different for here. So the sodium is the only one now that is just floating around, not doing anything in particular. for this particular reaction. So we can just go ahead and say we have acetic acid reacting with hydroxide to form acetate ion and water. So we're looking for the Kn, or the neutralization constant, for this reaction. And we're fortunate in that we can add reactions that we know the equilibrium constants, and we can get the reaction, we can sum them to the reaction we're interested in, and then we can find the associated equilibrium constant for that reaction. So that's exactly what we're going to do here. So I'm going to use acetic acid being reacting with water to form the acetate ion and the hydronium ion. Notice that this isn't exactly the reaction that you have up above, where we have the acetic acid with hydroxide. That's a neutralization. This is just acetic acid dissociating water, acting as a weak acid. We have the Ka over there on the right. The next one is just the neutralization reaction. Notice I just used hydronium, so it changes things slightly there for that equation, but all is the same as what we had before. So we're using the hydronium plus the hydroxide to form two waters. That, of course, we can look at as 1 over Kw, and that is 10 to the 14th. So if you remember, the sum of the reactions will give us the reaction we're interested in. Let's just see that for a second. So the waters cancel out. We're left with 1 water on the product side. And the hydronium ions cancel out. Adding those up, we end up with the equation that we're interested in. Okay? And one thing of note that we'll discuss in just a moment is we're left with a weak base in the acetate ion. We're left with water, which is just going to act as a neutral sort of, it's going to act neutrally in this. It won't contribute to being basic or acidic. So if you remember, if we sum the reactions, we have to do the product of the equilibrium constants. And so we end up with Ka times 1 over Kw, or Ka divided by Kw, and that will give us the neutralization equilibrium constant for this particular reaction. And we come out with 1.8 times 10 to the 9. And so 1.8 times 10 to the 9, or 1.8 billion, is a really big number. And so it's reasonable that we expect that this is going to go all the way to product. So you can see that it's justified that I used an arrow there instead of using a equilibrium arrow. The other thing I want to take note of is what I just mentioned earlier, the fact that we're left with acetate, which is a weak base. And so we don't expect in this case to have a pH of 7. If a weak base is present, then that thing is going to further react with the water that's present, and we're going to end up with a pH that is greater than 7. We're going to have a slightly basic solution. So now we want to talk about a neutralization reaction with a weak base and a strong acid. So the net ionic equation, and what we're going to use for this particular reaction, is just looking at ammonia, a common weak base that we use. So ammonia is reacting with hydronium ion to yield water and the ammonium ion there. So again, we're going to have to add reactions to get to this net ionic reaction, just as we did before. So we end up with NH3 reacting with water, and then that's going to form the ammonium ion and the hydroxide. Notice again, that's not the neutralization reaction, that's just ammonia acting as a weak base. It's got a Kb of 1.8 times 10 to the minus 5. And then we look at the hydronium reacting with the hydroxide, so we're using that first reaction that we used for the neutralization of strong acid, strong base, and we end up with 1 over Kw as the equilibrium for that. Cancel out stuff and add our equations here. We end up with hydronium ion plus ammonia to yield water and ammonium ion. And so exactly what we have up above. So now we can go ahead and do the product of these two, and it'll be just Kb over Kw will be our neutralization constant. And so we end up with 1.8 times 10 to the 9. Now in this case, you notice that we end up with a neutral water, and we end up with an ammonium ion, which is a weak acid. Again, that neutralization constant is 10 to the 9. It's still heavily favoring products. So what we can say is an arrow is appropriate in this equation. We don't have to use an equilibrium constant or equilibrium arrow. We can just say that this reaction is going to completion. And again, since we have a weak acid left behind, that ammonium ion, we can say that it's not reasonable to say we're going to have a pH of 7. We should have a pH that's lower than 7 and have a slightly acidic solution because we have a weak acid that's left behind after we do the neutralization reaction. So if I look at a weak base plus a weak acid, we'll just take our two ions that we used before, so the acetic acid plus the ammonium or ammonia, and we end up with ammonium and acetate ion there. If you're looking for the Kn for this particular reaction, we're going to have to start adding equations. We're going to have to use 3 in this case to actually get what we want, not just 2. So we have the acetic acid reacting in water, we have the ammonium or the ammonia reacting in water, and then we have the neutralization reaction that we have the strong acid, strong base. And so adding up all 3 of those, what we'll end up with is the reaction that we're particularly interested in, of the acetic acid reacting with the ammonia to create that ammonium and the acetate ion. And so that's no different from what we did before. We just summed 3 reactions. We're going to have to find the product of the 3 equilibrium constants. So this will be Ka times Kb times 1 over Kw. And what that will yield is 3.2 times 10 to the 4. So this is becoming a little bit more modest than what we had before. We went to 10,000 instead of a billion. And so this is becoming something that is more akin to something where you want to use an equilibrium constant as opposed to using an arrow to say that the reaction proceeds completely to one side or the other. This goes back to what we discussed last semester, or not last semester, last chapter, in chapter 14, when we were looking at if you mixed a weak base and a weak acid, what pH would you get? And it's the same thing here. It really depends on the magnitude of the Ka and the Kb. In this case, we have magnitudes that are equal to one another, and so we expect that the pH will be very close or equal to 7 in this case. But if the Ka was much stronger than the Kb, and was a bigger number, we'd expect it to be slightly acidic. If Kb was greater, we'd expect it to be slightly basic. So let's look at the net ionic reaction or equation for this strong acid-base titration. So which one of these 5 different options is going to be the one that gives us the net ionic equation we see above? So if we looked at the nitric acid and the ammonium ion, then I know that the H plus that I give off there is just going to go attached to the NH4 plus, and that's participating. So I should expect that one not to work. The only thing that's spectator ion is the nitrate. B is HF and NH3. Well, that's a weak acid and a weak base, and we shouldn't expect to have that strong acid, strong base net ionic equation. That was the only one that gave us this up above. HF and potassium hydroxide. That one could be a little tricky. You might think that one is, but the HF is predominantly in solution. It's still just HF, so they weren't floating separately apart. The hydroxide actually had to come and steal away that H plus from the HF molecule. And so in that neutralization, that is not, it's going to have to include the fluorine that's present, and that one is not going to have as simple of a net ionic equation. D, HCl and potassium hydroxide. That one works. Why? Because the chloride and the potassium were just sitting around the whole reaction. They didn't do anything. They didn't participate. They were just floating around because these things were completely dissociated the moment they hit water, because we have a strong acid and we have a strong base. And so those are going to yield the net ionic equation we're interested in. Go to E, and we look at HCl and the CH3 and H2. That one is also not going to end up giving us a clean net ionic equation, because that CH3 and H2 is going to pick up that H plus. It's going to act as a base, and it's going to be included in the net ionic equation. So anytime you have a weak acid or weak base, you're not going to get that net ionic equation. You have to have a strong acid and a strong base. So D was our correct answer. So another important equilibrium sort of effect is the common ion effect. And basically, this is another manifestation of the Le Chatelier's principle. And it just says that we have a shift in equilibrium when an ion present in the equilibrium is added to solution. So if we took this equation where we have the acetic acid plus the water to yield the acetate ion plus the hydronium ion. What happens if we were to take some sodium acetate and just start throwing that salt in there? So effectively, we have to look at this from the perspective of Le Chatelier's principle. You're adding a product. You're adding the acetate ion. And so if we're thinking about this in the context of Le Chatelier's principle, should it be nothing? Should it move to the right? Or should it move to the left when we add a product? Should be thinking that it should move to the left. So the common ion effect is nothing more than just our extension of the Le Chatelier. So let's consider in this clicker question a solution that has a weak acid, consider acetic acid, and it has a pH of 2.89. Which of these, if we were to add, which of the following would not increase the pH of the solution? Okay, and so if we added ammonia, what do you think? So that is a weak base. We would expect that probably to increase the pH of the solution if we are adding a weak base. I'm going to skip down to C, hydroxide. That is a strong base. Okay, we should expect that to increase the pH of the solution. D is sodium acetate. The acetate ion, as we mentioned, is something that is a weak base. So we should expect again that it's going to increase the pH of solution. E, sodium fluoride. Fluoride is one of those ones that I think is tricky to remember, but it is fluoride is a weak base as it's associated with the weak acid hydrofluoric acid. And so fluoride is going to act as weak base and it's going to increase the pH of solution. This question asks which would not increase it. That is going to be B because we're adding the ammonium ion, which is a weak acid, and it will decrease the pH a little bit, but it won't increase it. So B is the correct solution for this particular clicker question. So let's quantitatively take a look at this common ion effect. So we're going to compare the pH of a 0.1 molar solution of acetic acid, which yields a pH of 2.89, versus looking at the pH of a solution that we make from a 0.1 molar acetic acid solution and a 0.1 molar sodium acetate. So we're 0.1 molar in both of those species before we start. So what is the effect of having the sodium acetate present? What's it going to do to that dissociation into hydronium ions? And so if we go ahead and look at our equation here, it's just the acetic acid with water. We need to set up an ice diagram. So we end up with 0.1 and for the initial concentration of the acetic acid and the acetate. And we know it should move to the right since we had 0 of the hydronium ion to start with. And so we end up with a minus X and on the left, a plus X on the both species on the right. So we end up with 0.1 minus X, 0.1 plus X, and X. Now, this will give us the equilibrium equation of 0.1 plus X times X over 0.1 minus X. Now, X was small enough in the past equations to go ahead and use our approximation. We expect it to even be a better approximation here simply because this should stifle the amount of hydronium ion that's formed or the amount of dissociation that we're getting simply because we have that common ion present. And so we use our approximation to make this problem a little simpler, and then you end up with just 0.1 over 0.1 times X. That's going to approximate X. The hydronium ion concentration is going to be equivalent to that, and it's going to give us 1.8 times 10 to the minus 5 molar. If we go ahead and calculate what the pH of that is, we end up with a pH of 4.74. So without the acetate present, we had 2.89. With the acetate present, we ended up with a pH of 4.74. So basically Le Chatelier's principle worked. It moved the reaction to the product side. We got less dissociation. We got less hydronium ion present because we were adding that common ion, the acetate. We can go ahead and see the effects of this by looking at the common ion effect as we sort of add more and more acetate. So you can see we're starting with 0.1 molar acetic acid in this, and then we're just adding increasing amounts of the acetate solution, or the acetate in the solution. And what you see is basically this precipitous drop off of the amount of hydronium ion present as we add more and more acetate. And so we're shifting the equilibrium progressively to the left as we do that. And that's precisely what this graph is showing us here. So, buffer solutions. A buffer solution is something that contains a weak acid and its conjugate base. As a result of having both of those presents, not presents, it's not Christmas, having both of those present, it's going to resist drastic changes in the pH, because if we add some hydronium, there's going to be a weak base present to pick it up and react with. If we add a little hydroxide, there's going to be a weak acid present that's going to react. And so since we're not directly adding to the concentration of H plus or hydroxide, because it gets eaten up in a reaction in there, we're going to end up with something that resists changes in the pH. So let's look at some examples of weak acid conjugate base pairs. We got a HF and F minus, acetate and acetic acid, ammonium and ammonia. We could have dihydrogen phosphate, hydrogen phosphate, and I mean just a myriad of different other conjugate weak acid conjugate base pairs. So the first one we'll take a look at is looking at acetic acid with water, and it's going to react, give us the hydronium and the acetate. So let's look if we had a solution that we put both of those present. Okay. So we know that the one on the left is a weak acid, the one on the right is our weak base. And a buffer that's pretty decent is going to have a fair amount of weak base and a fair amount of weak acid. We want to be able to add hydroxide or hydronium, and we want it to be neutralized with one of those other species, as opposed to running out of one real quickly because you had an imbalance. If you have a fair amount of both, you're going to get a better result. So let's look at if we did an addition of hydroxide to the buffer. Well, the acetic acid is going to react completely with that. As we mentioned, that has a neutralization constant of 10 to the 9, so it's huge. And so it's going to react completely and just create acetate. Okay, so we're not really adding much to the pH of this because we are just creating acetate ion instead. And so the pH tends to move a little bit slow. If we add hydronium ion to the buffer, then what happens is we end up with a reaction where it's neutralized and we create more acetic acid. So in that case, we're not changing the pH by very much because we're just creating more acetic acid. We're not adding just directly hydronium ion. And remember, this acetic acid isn't going to dissociate that much. So as long as we have a ratio that of the weak acid and the weak base that remains close to what we started with, we're going to have a pH that's approximately close to what we started with. And that's the beauty of buffer systems. It keeps us pretty steady despite being jolted by some hydroxide or hydronium ion. This is crucial to almost every living system to have some buffer system that actually keeps the pH of it relatively constant. So one important property that we're interested in often is the buffering capacity of a buffer system. And that's just basically looking at characterizing how much of an acid or a base that this solution can absorb without getting a huge change, significant change in the pH. If you remember back, I think to lab 6, you did a titration in a buffer system that you had. And you looked at how many drops of acid and how many drops of base. You needed to either raise or lower the pH by a unit of 1. And so in effect, you were checking the buffering capacity of that buffer system. Of course, the buffering capacity of a system is going to depend on how many moles of the weak acid and how many moles of the conjugate base that are present. If we have equal volumes of the buffer, then a more concentrated weak acid and a weak base are going to give us a greater buffering capacity because it's going to have more moles per liter, right? If we have equal concentrations, however, then having a greater volume is going to give us a greater buffering capacity because now you have more moles present in that solution, and so you'll have a greater buffering capacity in both directions. So keeping that in mind, which of the following solutions is not a buffer solutions? So this is kind of tricky at first. So we look at the sodium chloride and the HCl. Well, the sodium chloride is not an acid or a base. It's not going to do anything. So that's just an acidic solution. So I wouldn't expect that to be it. So our qualifications are we need something that has a weak acid and a weak base present. So if I go ahead and go down to the acetic or sodium acetate and the acetic acid, that one, that's a buffer system because we have a weak acid and we have a weak base. We have the acetate ion and the acetic acid. It's just got a molarity of 0.1. The next one is ammonia and ammonium chloride. But the ammonium is the most important part of that, the NH4 plus. And so those two species are going to act as weak acid, weak base conjugate pairs, and those will serve fine as a buffer. Now, this D and E, I think, are a bit tricky when we look at this problem because it shows sodium acetate and then it shows hydrochloric acid. So how we already said A was not a buffer. So unless this problem is written incorrectly, how is this actually a buffer? Well, what is the HCl going to do with the acetic or sodium acetate that's present? It's going to react and protonate that sodium acetate. So 0.1 molar of that sodium acetate is going to end up reacting with the, given we have maybe 1 liter of solution. And so 0.1 molar of that HCl is going to protonate that sodium acetate, and we'll end up with 0.1 molar of sodium acetate and 0.1 molar of acetic acid after these two react. So this is just a means of actually producing a buffer if you don't have the conjugate pair of the acid or the base using HCl or something like sodium hydroxide. So the next one is exactly that same sort of situation. We have 0.2 molar of acetic acid. We're going to react it with that sodium hydroxide. And so we are going to end up with 0.1 molar of sodium acetate as a result of that reaction, and now we do have some acetic acid, some sodium acetate present. And so because of those last two, you're creating the conjugate pair. Those are both buffers. So A would be the correct answer there, as it is certainly not a buffer. And I guess this is going over what I just said. I forgot to add these in there. And so yeah, we should end up with 0.1 molar of HA and 0.1 molar of A minus. Same thing with the other one there. Okay. So one of the important equations that makes our lives a lot simpler to figure out the pHs of buffer solutions is the Henderson-Hasselbalch equation. And so to look at where the origins of that equation are, let's just take the weak acid reacting with water to form our hydronium and the weak base A minus. So we have the acid HA, the base A minus. If we were to write the equilibrium equation for this, or write the expression for the equilibrium constant, we look at the hydronium times A minus over HA. If we go ahead and take the negative log of both sides of that reaction, we're going to end up with negative log of Ka equals the negative log of that expression, H3O plus A minus divided by HA. Now remember, the rule of logs, we can sort of separate that product in there. And so what I'm going to do is I'm going to rewrite that as minus log of the hydronium ion concentration minus log of the A minus over HA. Now there's a couple things we can start recognizing. What do we consider that minus log of Ka? What's the pKa? And what's the minus log of the hydronium ion concentration? That's the pH. So let's express that in a little bit different fashion. pKa equals pH minus log of A minus over HA. Now to get us in our final form, we just need to move the log over to the left-hand side and solve. And so we end up with pH equals pKa plus log A minus over HA. That is conventionally known as our Henderson-Hasselbalch equation. And so this is just a convenient way that's going to help us prepare buffers and figure out the pH of a buffered solution. So let's take a look at using this Henderson-Hasselbalch equation. So in this particular example, we're going to look at vitamin C or ascorbic acid in a buffered solution. So we have a Ka for ascorbic acid that's 8 times 10 to the minus 5. And it asks us what's the pH of a solution that's 0.2 molar in ascorbic acid, which is going to be our HA in this case. It's a weak acid. And 0.4 molar in sodium ascorbate, which is going to be our weak base, or A minus in this case. So I'm going to first go ahead and calculate what the pKa is, and it's going to give us a value of 4.1 when we do the minus log of that Ka. So now applying this to the Henderson-Hasselbalch equation, you see the pKa is in there, so I still have that minus log of 8 times 10 to the minus 5. But now I have to add on the plus log of A minus over HA. Remember, A minus is going to be our ascorbate, and that's 0.4 molar, and that's on the numerator. And then the ascorbic acid is going to be 0.2 molar, and that is going to be on the denominator. That's our HA. We calculate a value of 4.40 for the pH of that solution. One thing to take notice of here and look in a little bit more detail is to sort of ask ourselves, when is the pH going to be the same as the pKa? Because this one's a little north of that, right? It's a little more basic than the pKa is at 4.1, pH is at 4.4. So when are those two values equivalent? Well, if you remember a log, if we do the log of 1, we get 0. So when this ratio is 1, we end up with 0. So that will leave us with the pH equaling the pKa. And that is only going to happen when our concentrations of the acid and the base are equal. So what's important there is now we talked about buffering capacities. If we have equal concentrations of both, then we have equal buffering capacities in both directions. And so adding about the same amount of acid, the same amount of base will, it'll yield a similar change in both directions. And the other thing that is important is that if a ratio is sufficiently different than 1, then the pH is not going to be close to pKa, and you're going to end up with a system that doesn't have very good buffering capacity in one particular direction. So often one thing that we have to consider is that if we want to, say, have a solution that we want to be at a pH of 9.7, then we need to find a weak acid that has a pKa that is approximately 9.7, and then it'll be able to buffer equal in both directions. So in this particular solution, if we said what pH is ascorbic acid good at buffering around, the answer would be 4.1, because that's where the pH equals the pKa. And so we could have equal buffering capacity in both directions. So this, in effect, is something that is used a great deal in figuring out how we prepare a buffer for a given pH. So now let's take a look at another problem. We're going to look at part A, which just says what is the pH of a buffer solution of 0.45 molar ammonium chloride and 0.15 molar in NH3. And then it asks us how would you prepare a buffer of this system with a pH of 9. So the first thing is you'll probably be given the Ka for this, or the Kb. You'll be given something that what you need to eventually get to is the Ka or the pKa. And so for ammonia, you're probably going to be given the Kb. It's more predominantly sort of associated with being a base. And so if you're given the Kb of 1.8 times 10 to the minus 5 molar, you could calculate the pKb if you wanted, and I'll give you 4.74. And remember, there's a number of ways that we could arrive at the Ka and the pKa here. And so the way that I would do it if I wanted to go from Kb to Ka is I would use the Kb times the Ka equals Kw. So you end up with 10 to the minus 14 over 1.8 times 10 to the minus 5. And then that would yield that 5.6 times 10 to the minus 10 for the Ka of ammonium. And then the pKa, we could either just do minus log of that 5.6 times 10 to the minus 10, or we could use the fact that pKa plus pKb equals 14. And so then that would be 4.74 plus pKa equals 14, and that would end up, actually in this case, yielding 9.26. It's just a little bit off on the sig figs or the round off error there. But nonetheless, we end up with our pKa from one of those approaches. And so now that we have the pKa, I can go ahead and plug it in the Henderson-Hasselbalch equation. And so I have the pH equals pKa plus log A minus over HA. Plug in that 9.25 value I get for the pKa plus log of A minus, and in this case NH3s are A minus, so 0.15 molar, divided by the 0.45 molar of the ammonium chloride. And so we end up with a pH of 8.77. So that's part A. So how do we prepare a buffer that's going to have a pH of 9? So we know what the pH we're looking for. We know what the pKa is. And so now we're just looking for the log of A minus over HA, or eventually that ratio of A minus over HA. So setting this up, subtracting 9.25 from both sides, and then flipping it, I end up with log of A minus over HA equals negative 0.25. Now, in order to solve for this, I have to raise both sides by 10 to the power of, and so I end up with A minus over HA equals 10 to the minus 0.25. That equals 0.56. And so that tells me that for every 0.56 moles of base, we're going to need 1 mole of acid to achieve that pH of 9. And so if we wanted to prepare a buffer in this fashion, we could go ahead and add 0.56 moles of NH3 or ammonia, and we could add 1 mole of ammonium chloride and to just a 1 liter volumetric, and we'll end up with, after we fill it to the 1 liter mark, stir it a bit, we'll end up with a buffer that is buffered around a pH of 9. Now, of course, since that is a little south or a little bit lower than the pKa, we know that it's not going to buffer as sufficiently in one direction. Which direction is that? So you've got 1 mole of any ammonium chloride and only 0.56 moles of ammonia. So we know that if we're down there, we don't have as much ammonia present, and that won't be able to neutralize as much acid. And so it's going to suffer in its buffering capacity one direction. But maybe it's suitable for what we're doing. So looking at this problem, it says if we have a solution that's prepared by mixing 40 milliliters of 0.5 molar sodium acetate and 60 milliliters of 0.5 molar acetic acid. In this case, we just have to be careful. Our final solution is going to have a final volume of 100 milliliters. So we need to calculate basically what that new concentration is. So if I just go ahead and calculate the moles of acetic acid present, I end up with 0.03 moles of acetic acid, just using the concentration. Remember, just diluting or something is not going to change the moles of that. And if I take the sodium acetate there, I have 0.02 moles of sodium acetate. And more important is the acetate ion. Sodium's just spectator, just around. So now what I'm going to do is I go ahead and I know my pKa, because in the bottom right there, middle right there, it says pKa is 4.74, and I just do plus the log of the 0.02 mole of the A minus, or the 0.02 moles of the acetate, divided by the 0.03 moles of the acetic acid, and I end up with a pH of 4.56, and you see that lines up nicely with A. So one question you might have is, why did I leave out the concentrations here? We have concentrations in the base over the acid. Well, the base is described as the number of moles per volume, and the acid is the number of moles per volume, right? And so those volumes can cancel out. So if you want to just use the moles, you can in this equation, and it'll be just fine. And so, yeah, the math is worked out there on the bottom right. You can see you just end up with moles of the base over the moles of the acid. And that's precisely what I used there. So what we're going to cover in the next lecture to a much larger extent, and it's going to focus on, is just titration curves. And so you've done several titrations in the lab, and you know hopefully that titration is basically just this procedure for determining the concentration of some solution by using some standard solution that's usually in your burette. And so typically we have their standard in the burette, and we put our unknown in the Erlenmeyer flask, and we mix them until we reach some equivalence point, at which point we can calculate, using the volume that we've added from our standard solution, how much of the unknown that we have present in the Erlenmeyer flask or solution below. So the nomenclature that we need to be familiar with is the titrant is just our standard solution. It's sitting in our burette. And the titrand is the solution of unknown concentration, and that's usually going to have an indicator, or for instance, if you're doing a precipitation reaction, you'd use basically the cloudiness to indicate when the reaction had reached its equivalence point. So a number of different ways, but usually they'll have something present that we can detect when we're at the equivalence point.